Hey everyone, let's keep going through some thermodynamic processes. Before I get onto this, I'm just going to leave this up. You write it down. Just a reminder that, let's see, I'm having that due date for your extra credit. It's on the 16th. You hand that in whenever you get it done. Do as much or as little of it as you want. Also, the homework I've assigned is a bit larger than most other homeworks. I pushed the due date back quite a bit. I will warn you, don't put it off to the last day. It probably will be overwhelming if you do that. So you go ahead and get started on that. For today, we've talked about temperature, creating a thermometer, and how things might heat up. Now let's get into these sort of gases and fluids that we've been, talking about. Maybe they start to expand. We've seen that metals, solids. We know that gases, if you heat them up, they'll expand. Maybe we want a way to calculate or predict how much something may expand or contract. When you change the temperature, or maybe you have a gas in a container and you want to add more, but you don't know if the container can hold it. One, container might not be rated for it, but two, maybe the gas itself will heat up if you try to contain it in the container. So the way we get around this, the way we sort of simplify this huge problem is we can say most gases can act as an ideal gas. This is something where we know that gas and sort of fluids, they're made of these individual particles, and we know that they're going around hitting the walls of the container. But for an ideal gas, we're saying that they're always moving randomly. They're always not necessarily interacting with each other, so they're not hitting each other. And it's sort of evenly spread out through the whole container. That's not typically true with most fluids and gases. These things are small little projectiles. Sort of the gas or the helium in a balloon, you shake it up, and you can expect some of the helium might start to shake. Have this sort of ebb and flow inside of that helium balloon. But for simplicity's sake, for the grand scheme of learning how to do these things, we can treat most gases as what's called an ideal gas. An ideal gas we could predict with this equation right here. PV equals nRT. Stuff in this chapter, I think mostly in this chapter, you'll see like a repeat if you've already had chemistry. So this is going to sound like a broken record today if you've already had chemistry, or maybe you had chemistry today. You've already gone over this. I've added the terms up there in case my pen doesn't work. So P for pressure, volume. I always try to make these when I'm writing them down. I try to clarify that they're capital. They're capital letters, so I don't mistake it for velocity. That's a real easy one to mistake it for. N, lowercase n, that's the number of moles of gas. If you don't quite know what that means, I'll explain in a minute. R is a universal gas constant. So this is like, gravity is sort of constant here on Earth, everywhere on Earth. If you study things that are moving out in space, there's this universal gravitational constant that keeps like stars and galaxies together. So it's just a thing that applies to everything. For this universal gas constant, it's just something that is just a number that's the same throughout every type of gas. And I have that here. You could use it in a couple different units. I'm going to put them both down. So we have one version is 6. Sorry, already wrong. It's an 8.31 joules per mole times Kelvin. The other version of this, it all depends on what units you're using for your problem. Maybe you're using joules, maybe you're using calories. I'll get to that also in a minute. Maybe this other version of the universal gas constant is more helpful for you. 0.0821 that's liters times atmospheres over moles times Kelvin. So there's also the tricky thing with pressure. I think there's way too many units for pressure, personally. There's pascals, there's atmospheres, there's millimeters of mercury, there's bar, there's torr. They just create more and more, it seems like, every day. For this class, we're just going to use, for pressure, it's typically just going to be like atmospheres. So the unit of atmospheres, ATM, and pascals for pressure, PA, for pressure. Volume, that's typically liters. That's an SI unit of liters. Or you could do cubic meters. And temperature for this section, since we want to have this range that is always the same, we're going to use Kelvin, since 0 Kelvin means absolutely no energy. And we want to talk about how much energy something has. So for this chapter, actually for 3 of these chapters, anything with temperature, we're going to use Kelvin, just so we could get used to it. And I think that's all I wanted to add on this slide. Yeah. Okay. Now, let's see. What are some funny things that popped up here? When we start talking about, these small things that are in gases, they could be individual particles or molecules, any of these tiny things flying around. We're considering them an ideal gas. They're all random. However, do you ever think about, still here? It is. How much air is in a balloon? How many individual air molecules are inside of that? It's a number that I don't want to have to keep counting. Maybe I don't want to count every single individual particle as it collides with the surface of the balloon. That's a headache. So what's been created is Avogadro's number, not Avocado's number. Avogadro. So this is just a certain value that works well with chemistry, mixing units on the periodic table. So Avogadro's number is, it's written like this, 6.022 times 10 to the 23rd. And that's that many things per mole. So I'm going to put the units as, you got to make sure you clarify in your notes what I'm doing. Things per mole. So what do I mean by that? Well, let's say, yeah, first I can say, what is a mole? I'm introducing this weird new unit of moles. It's not the small thing that lives under the ground, nor is it the guy in Animal Crossing. Does anyone know his name?
Rossetti, right?
Rossetti, yeah. So, quick side story. Mr. Rossetti right there is a character in a game called Animal Crossing. And if you happen to, I'm just going to call it cheat in the game, Mr. Rossetti pops out of nowhere and starts being really frustrated with you. He looks like that. And millions of kids everywhere were terrified that their game is now actually talking to them. This is on like a Nintendo 64 before, our era. So, not this type of mole. We're talking about the unit. It's just a size. It's just a number. It's just that number right there. So, if I have 1 mole of donuts, that just means I have diabetes. No, I have 2 times 10 23rd donuts. Same thing with particles or atoms or molecules, anything. It's just a size. It's just that number of things. 6.022. In this case, it's particles. Right, maybe we want to go from moles to maybe a specific mass. So in the previous slide, I can't go back. It's gone. I'll have to write on the board later. It was PV equals nRT. So number of moles is important. That factors in, the mass of the material. Maybe it's a gas of hydrogen versus a gas of helium. They have different masses up there on the periodic table. Maybe I need to consider that. So, the number of moles, this is lowercase n, number of moles, is equal to its mass over its molar mass. And so, the way this works out, the book walks it through a bit more eloquently than I can do right now. But pretty much, those values on the periodic table, you see for like hydrogen, it's 1.0794. It doesn't give a unit right there. So the units is 1.0794. The unit is U. And that's molar masses. So what it turns out to be is that if you want to figure out a certain mass of, I don't know, carbon, say you have 16 grams of carbon, or no, sorry, let me do this. This will make more sense. So let's find what carbon is. I can't see. 12.011. So for carbon, so in this case for carbon, the units on the periodic table by using the Avogadro's number of moles, I'm able to just like directly go into grams. Okay. All right. So now let's do a sample of this. Let's say an ideal gas, doesn't matter what it is at 20 degrees Celsius and a pressure of 1.5 times 10 to the 5th pascals, and is in a container that's a volume of 1 liter. Determine the number of moles of gas in this container. All right. So first, we do all of our conversions. We know that at Celsius, we know we're going to need it in Kelvin. We're going to have to do the 1 liter, the cubic meters. So let's do those real quick. Let's see. We'll do that first part. I'm going to do it on this slide, and then I'm going to do the second part on the next slide. Okay, so we have temperature is, we want it in Kelvin, so whatever the temperature was in Celsius plus 273 all right, so it's just plus 20. So it's 293 Kelvin, 0.15. All right, now all we have to do is use that ideal gas, it's called the equation of state formula. We use that ideal gas formula that I was given earlier. It was PV equals NRT. All right, we're just solving for that first part, part A, number of moles in the gas. Number of moles of gas, sorry. Solve around, shift this equation around, we get all right, and we could just keep going from here, insert the values, and let's see, for we want to use, that's pascals, Kelvin, that cancels, that cancels. Okay. So we have 1.5 times 10 to the 5th pascals. That's me converting the liter into cubic meters. And we have 8.31 joules per mole times Kelvin. It's actually, 0.15. 0.15 Kelvin. Okay. Running through this, we get a certain number of moles. It's equal to, we get N equals 1/6 And the unit is just like a lowercase mol. So I don't really like that. I'd rather just spell moles. So we have answered part A. Awesome. So we figured out how much gas is in the container. So you can imagine that's like, I can have the amount of gas that's in this balloon. But then I can just sort of stretch the balloon to be bigger and keep the same number of molecules in here. So always sort of separate the amount of gas versus the volume. So the volume doesn't mean that's the amount. So N is the sort of amount of stuff that's crammed into this volume. Okay. Part B. Let me write this down somewhere. I'm going to write it over here. 6.16. Just because I'm going to go to the next slide. -2. Okay. There we go. So now part B, the gas pushes against the piston. So let's say it is the case where the balloon, or in this case a container with a piston, is going to increase the size of the container. So imagine if I sort of just grab this balloon and I stretch it, and I make this twice the volume. That's what the question is sort of phrasing. So imagine if this is in a, I don't know, like a cylinder in your car engine or something, where the piston will pull back and increase the volume, but keep the same number of moles of gas in the chamber. Okay, gas pushes against the piston, expanding to twice its original volume, while the pressure falls to atmospheric pressure. So whenever something is phrased like that, they say they are meaning it is now at 1 atmosphere. So that's the pressure that Earth's atmosphere is pushing down on us right here at sea level, technically. And I've got the little conversion for you guys right next to it. So 1 atmosphere of pressure is equal to 1.01 times 10 to the 5th pascals. So there's way too many units for pressure. I don't like it. All right, so in this second part, we're finding that final temperature. All right, so we start at, I'll say initial. We start at 1 liter. And then at volume final, we've doubled it. So now we have 2 liters. Okay, so there's an initial state and there's a final state. That's what I've sort of devised from this problem here. So I can calculate the temperature maybe before, the temperature after. And they give me the temperature before, when it was at that original state. So I could use that. So let's see. I can say use a ratio of the initial and final state. So we have, let's say, the ideal gas equation for its final state and the initial state. Let's do it like this. We say the initial pressure and the initial volume is equal to nR times the initial temperature. And all of that, or I should do it, technically I should do it on both sides. Let's do it like this. The final volume in R times the final temperature. Why don't I have an initial and final N and R? They're the same. It's the same number of molecules in the container. So that's the same. And R, that's just a constant everywhere. So those don't have initial and final cases, which means I can just cancel them out right now. So let me do that. All right, we're left with, let me move over here. All right, now we can see we're really close to just having the final temperature on one side of the equation by itself, solving for that final temperature. Let's do that. So this, you got to flip it around and multiply over some stuff. But eventually we get to something that looks like this. That's going to be P final. Oh no. No, yeah. Something that looks like that. Let me make this a bit more clear. And I changed it to 1 and 2. Let me final, initial. There we go. Okay. We're almost there. We just have to insert what we found. So the final pressure, that's going to be it sort of reducing down to 1 atmosphere. Its final volume, well, in this case, I haven't converted to cubic meters like I did in the first part. And at this point, maybe you see that I don't have to liters. It's because on the denominator, I'm also going to have liters and unit of pressure. So they're going to cancel. O okay. So we get, sorry. Spoke too soon. We have that initial temperature on the outside. So all of these units in this sort of in this ratio cancel with each other, leaving behind the unit of Kelvin. That way we're able to find that final temperature of 395 Kelvin. All right, let's take a minute. I'll give you guys a minute to finish copying that. You see? So what this is saying is that this object started out with a temperature something like that. And then ended up something like that. So it increased temperature by over 100 degrees. So if I have a gas, I'm not saying it's this gas or the air, but maybe the reason for this sort of expansion, I have 1 liter, let's say it's air, and then I increase it to be 2 liters. Let's say 2 liters. Maybe the reason was me heating this gas up. Just heating the gas up makes it expand to twice the volume. So I could have worded the problem differently to say that I'm heating this gas up and it expands. How much volume does this thing expand to? And for all for all ideal gases, they are sort of this predictable thing where heat something up, it's going to expand. Cool it down, it's probably going to contract some. I should say on the most part. Okay? All right. That's pretty much, let's see, chapter 10 or so. So there wasn't a whole lot in there. We're going to move on to chapter 11. Same, general thing. I'm grouping these all together. So we have an idea of how gases might react when you heat them up, cool them down. We know how to predict, their behavior. But something still about objects that get hot. Why does one thing pass, this temperature to another thing? So I talked a bit in the previous chapter to get you guys sort of used to it, this thermal contact, where something's sort of either in direct contact or right next to each other. Maybe they're just sort of in the same space. They are able to transfer energy. Let's sort of look more closely at this energy transfer. This is something called heat. So heat is the transferring of energy. Whenever you heat up your coffee, you are adding energy into your coffee. So the process of adding is heat. So heat is an action word. Should also say that heat will always move from hot objects to cold objects, because things that are considered hot have more internal energy. So again, I wish I had 2 of those spring cubes, so I can show shaking one thing will flow over into the other less energetic object. So you imagine you have a solid that is very energetic, sort of shaking all over the place. That means it's very hot. you place it next to something that is cold, it's not shaking, wiggling, whatever you can imagine, the energy is going to flow into the less energetic object. So that's why if you, I know I always, when I was younger, had like a parent or something say like, you're letting the cold out of the fridge. That's not technically true. You're letting the heat into the fridge. So you could correct your parents whenever you have that debate. I'm sure they'll love it. Yeah.
So is that like the copper lab we did?
This is like the copper lab we did. We're going to get to specific heats probably sometime today. Yeah. So that internal energy, how much energy an object sort of can hold on to, whether it's you threw it really fast, it's like something was spinning, it had rotational energy, maybe I don't know, it's a spring and you're stretching it a whole lot and you're increasing that elastic potential energy. Things can store that energy, so whether it's kinetic or potential, and contain it as what I'm just calling a broad term internal energy. So stretching that spring by a whole lot might keep the spring up, might increase its temperature. So internal energy is just a, sort of a catch-all term. It says that this thing, through some sort of method, is holding on to some energy. Let's see. What do I want to do with this? We have that. Okay. There you see, we're almost there. We have thermodynamics. This was back before we knew that heat was transferring of energy. We just sort of had chemistry, and it was in the lab way over here, maybe in that other wing of the hall. And they did their own experiments that were dealing with things heating up and things cooling down. And they just called it Q. People doing physics experiments are over here doing things like rolling a ball or rolling a cart. They're just like lifting things up. They're calling that energy, and they define kinetic and potential, and they call those joules. So these two sort of ideas sort of created separately on what energy is. And typically in this area we call Q the internal energy, or the energy of transferred by heat. So, like I said, we had two different areas of science working on energy, each thinking they were like separate things. So people heating stuff up over here, they're like, oh, that's a very unique thing that's happening. People over here developing joules, stuff like that. So traditionally, people had to come up with this idea for, or a unit for energy. They said, let's call it a calorie. It's a lowercase c, calorie. It's defined as the energy needed to raise 1 gram of water by 1 degree Celsius. All right. You might think it's something like your food that you have. It says calories, same thing. Technically, sure, but there's a difference. This is not that. The calorie in food is technically, with a capital C, is technically a kilocalorie. So it's 1,000 calories. And I think the reason they did this is because people were afraid of just how many calories are in food. How many regular lowercase c calories are in food. So let's make those values smaller, and people won't be afraid of the large numbers. That's my theory. So when you see something that says 25 calories, that's actually 25,000 lowercase c calories. That's what the unit calories is. And since all energy is technically the same, once everyone was agreeing that, okay, we're raising the temperature of water, that's energy. I'm classifying it as energy. The people doing physics are like, well, I'm like looking at gravitational potential energies. That's also energy. Then everyone agreed, said, okay, we could just start using joules from now on. Having these various different units for energy. Energy is one of the keystones of understanding the universe. We need to have a consistent unit. So we're going to call it joules. So, let's see. It's right here. I'll put it right here. 1 calorie. And I'll try my best to make it look different. 1 lowercase c calorie is equal to 4.186 joules. All right. So, let's do a little problem that I finally figured out. I could just look at the example problems in your book. This is in your book. A student wants to figure out how much work they have to do in order to burn off their breakfast. So they had a bowl of cereal containing 3.2 times 10 to the second calories with a capital C of energy. He wishes to do an equivalent amount of work in the gym by performing curls with a 25 kilogram barbell. How many times must he raise the weight to expend that same amount of energy? And assume he's lifting it just vertically, just like straight up, straight down, by 0.400 meters. That's like 40 centimeters, not too far. Okay? So, I'm going to take the breakfast. I'm going to figure out how many calories were in it with a lowercase c. Then we're going to convert it to joules because that's the more useful unit of energy for us. So let's do that. Let's figure out how much energy was in that breakfast. I'm just going to say, E for energy. It doesn't quite matter right now. This is calories. Okay, well, we start with that. We start with 3.2 times 10 to the second calories, capital, and we need to convert it to lowercase calories. So I could say this is kilocalories to regular calories. And this is the lowercase c-a-l. So that's the conversion rate. And then we're going to change it into joules. So there are 4.186 joules in 1 regular calorie. I'm just going to call them regular calories and not lowercase calories. Okay. So those cancel, those cancel. We're going to be left with unit of joules. So breakfast was 1.34 times 10 to the 6th joules of energy. Some kind of internal energy. It was probably chemical energy in the sugars and whatnot. All right. Now, I think I have a double slide of this one. So I'm going to do the same thing where I clear it and go to the next page. I'm going to write down total amount 1, 3, 4 joules. Okay. All right, everyone good? All right. Now we need to figure out how much work they have to do in order to burn that much energy off. Okay. Work is the change in kinetic energy and the change of potential energy. Let's do work is the change of kinetic energy plus the change in potential energy. And let's see what all that's happening is this guy's going from down here and he's lifting this bar up and then back down. It doesn't give us like a velocity, so we don't need to like worry about that. And also I'm going to assume that it takes as much energy going up as it does going down, just because that makes the problem easier. And I think they could have worded it a little better. So, certain amount up, the same amount back down. Okay, so we're only looking at how this thing is changing its potential energy. I'm lifting it up, it's getting a bigger potential energy, lowering it back down. It's the same path, so it's the same amount of energy again. So the change in potential energy on the way up is just one of these. Then if we want to look at the total energy for like one repetition, we have to go like this. So I'm going to write this also so we can remember. Assume spend the same amount of energy lowering the bar. Okay, so we have this energy that needs to be burned off needs to be equal to like a number of repetitions times this certain like path. They're increasing the potential energy and then decreasing. It's that path, but twice. So, let's see. Let's solve for the number of repetitions they have to do. That's what it's pretty much asking for. How many times must he raise the weight? Number of I know we just had a lowercase n in one of the equations, so I want to clarify that all right. So pretty much we have the mass, we know acceleration of gravity, we know how much height they're raising the bar and lowering it back down. And I've written down the amount of energy that he has to get through. Kilograms and he raises it by 0.04 meters. Sorry, 0.400 meters. Turns out he has to lift this bar up and down, so that's 1 rep. He has to do that 6.84 times 10 to the third times. So that's what, 6,840 times, or reps, or whatever you want to call them. Just for the breakfast. It wasn't even like a great breakfast. It was just cereal. I like in the book, if you read further, it's like, why do we even lose weight at all? Like how many reps they got to do? Well, it can turn out like our body doesn't always absorb all of the energy from the food we eat. We actually aren't that efficient absorbing energy. So if we did absorb all of the energy in like milk and cereal, we would only need to eat like once a week. So, yeah, this is a sort of a neat way to figure out something useful in like exercising and stuff like that. There's also like our muscles, our organs also need to use some energy. So this is actually helping us. Need to use energy just to live. So if you guys look this up, you can go, I don't know any websites that have it. You could probably find one. You can look up the basic metabolical rate, and you could actually see how much energy you take in order to just live. So just sort of like lounging and laying on your bed, you burn calories, you burn some energy. Yeah, that's pretty ridiculous. All right, is that and that? Let's see. I think I only got a couple more left. So I looked at raising the temperature temperature of water, what about other objects? So every substance has a unique amount of energy they need in order to be raised by 1 degree Celsius. So whether it's the material in this table, material on the floor, the air in this balloon, or maybe even like the metal in the doorknob, everything slightly different material, so it needs a slightly different amount of energy to raise its temperature by 1 degree Celsius. You guys are in my lab class. Pretty much this and the next slide will be a repeat. So, specific heat is a description of how easily a material can change its temperature. So, whether it's the wood in this table, metal in the handrail, every material changes temperature a little bit, easier or more difficult than another. That is sort of a simplified way of thinking of specific heat. What I've also told my lab class is to think of specific heat as thermal inertia. So, inertia for things that move, it's an object's resistance to change and movement. Thing at rest wants to stay at rest. Thing's moving, it's move. So, how easily can you get that thing to move? How easily can you get this table to warm up? Same type of thing. So, we can look at how much energy it might take. And that's just the change in the energy, this change in delta Q, change in energy. And we have the mass of the object and the specific heat of that object. Specific heat is a lowercase c, and multiplied by however this object changes temperature, delta T. Capital T is always temperature. Lowercase t is always time. What are some examples of high and low specific heats? Well, one of the most common, things in the universe, water, has a enormous amount of, or an enormously large specific heat. It does not change its temperature easily. Significantly higher than like any type of solid. If you've had the lab, you've already gone through this. But you imagine you're going to the beach, and the ocean is almost always cold, no matter what time of year. The sun is constantly pouring energy into the water, but water itself has a very high specific heat. It doesn't like changing its temperature. It doesn't change very easily. So, if we want to do any type of, experiments, or calculations, maybe you want to figure something out with a temperature or with energy, we need to go through a method of calorimetry. And this is a method of looking at how much energy is in a system and sort of making sure it's a lone and perfect isolated system that's away from everything else. And this thing is going to be isolated and no energy is going to escape. Right. As soon as we have energy leave into the environment, then we have, temperatures changing, and our experiment is being ruined by the second. So, say we're given two objects, or two systems, I should say. We have one hot system and one cold system, and we want to mix them together. We need calorimetry to make sure none of that energy leaks out and goes somewhere else, because we want to calculate where the energy is going and what kind of temperatures are going to be resulted in. Or maybe we want to find a specific heat, or maybe we want to find the mass of something. So calorimetry is very important in us trying to track the movement of energy through temperature and heat. Right, so saying if we do it perfectly, this is what we'll get. And I'll take a minute, let you guys this down. So what these equations are, they're saying that all of the energy of that hot system, however it may change, and all of the energy of that cold system, however it may change, none of it's going to leak out into the environment. I'm going to do it perfectly. That's why I set it equal to 0. And so what is resulted in is we have this thing where it's minus delta Q hot equals delta Q cold. So that's saying, however the hot thing changes, however much energy the hot thing loses, the cold thing will gain. That's why hot has a minus sign in front of it. If you want to think of it that way, that's fine too. All right, we'll do one more thing and we'll be good. Okay, I'd say we don't have to write the whole thing down. You can write the key things down. So I know it's a lot. So we start out with a very hot brick of an unknown metal. It's 10 kilograms. And we need to cool it right away. Think like you're a blacksmith or something. You have like a sword. It's made out of something. You need to cool it down really quick. You place it in kilograms of water. And the initial temperature of the metal is 90 degrees Celsius. Initial temperature of the water is 25 degrees Celsius. And immediately after you mix the two, it reaches this sort of final equilibrium temperature where both objects are the same temperature. The hot thing cooled down, the cold water heated up, and it's at 28 degrees Celsius. So what is the specific heat of this metal? And the reason we're using that is because maybe we could use the specific heat to help identify the metal that's in this thing. So what is this likely to be? That's why I have the table off to the side. So pretty much for a calorimetry problem, we start almost always like this. What's the hot system? What's the cold system? So the thing that was hot and is changing energy is the metal. And so, I don't know, I'll call it, sub M for metal, or unknown metal. Maybe I'll call it U. We'll see. So this hot thing, I have to look at the change of energy of that metal. Let's call it M for metal. And the cold thing that changed energy, is the water. So I have to look at the change in energy of the water. Okay, at this point I can just fill in the values I know, because I know delta Q equals MCAT. That's what they say to sort of remind you. We have the equation of energy. I'll put it down here. It looks like delta Q equals MCAT. So I can just fill this in with the values I know. So the mass of the metal, the specific heat of the metal, and the change in temperature of the metal. That was that hot system. In the cold system, it's only one thing, the cold system. We have the mass of the water, specific heat of water, the change in temperature that the water underwent. So it says find the specific heat. We can just solve for it right now because all the terms are out and sort of laid out in front of each other. I'll put it over here. The specific heat of the metal, let me divide over these other terms, is mass of the water, specific heat of water, change in temperature of the water, over mass of the metal, change in temperature of the metal. Okay. So how much water was originally there? 20 kilograms. The specific heat of water. In this instance, this is the table I'm using. Those are the units I want on my table. So I'm saying that this is 4,186 joules per kilogram times Kelvin. Okay. And change in temperature of the water. So it went from 25 to 28. So final minus initial, that's only 3 degrees Kelvin. So it's the same, but in Kelvin. Sure. Over mass of the metal is 10 kilograms. Change in temperature, it went from 90 to 28. Let's see, what do I have? I didn't write it down. 62. So it went down 62 as a minus 62. And that's how it cancels out that other minus sign. 62 degrees Kelvin. We have a specific heat of this unknown metal. 405 joules per kilogram times Kelvin. So what is this metal likely to be?
Copper?
Copper, is it closer to copper or iron?
Let's say iron.
All right, it's in between that. So that means it's not a pure metal of those types. So either there's a chart that has an alloy, a mixture of metals, or maybe I did something wrong, maybe my experiment was wrong. But in this case, I'm going to say it's a mixture of metals. I'd say it's close to iron. That's 448. Copper is, yeah, it's a little closer than copper. What is, the next one up is glass. Yeah, definitely not glass. All right, cool. But doing this calorimetry sort of problem, just looking at how energy is going in and out, I could figure out the type of material of something I completely had no idea what it was. All right, and I think that's all I'm going to do for today. So, let you guys go. Reminder, get that extra credit done, and don't wait around for the homework. All right, I'll see you guys later. Have a good weekend.